Right, the section B on the AS exams. In the AS exams, not the A-level exam, but the AS exams have section B, which is the synoptic style questions. Right, and as you can see here, the section B in the AS papers can be on any topic. And here we have a mechanics question. Now, the synoptic questions, which are going to be on any topic within physics, for you guys, is going to be your paper 3. Okay, it's going to be your paper 3 next year at the end of year 13, and that's called General and Practical Principles in Physics. So that's the big paper. I think that's the really long paper, but that's all your synoptic questions, which can draw from any topic that we've studied over the 2 years. But anyway, let's have a look at this question. Right, so it's about application of knowledge. We have the Charpy test. Okay, used to be used by scientists to measure the fracture toughness of material. Right, so it's a simple pendulum. You got this thing here, which is let go and it swings. Now your sample of material is here, and you keep dropping it from increasing heights until the sample fractures. Okay. Now the maximum height you can drop it from at which it fractures. Okay, that can be used to find the fracture, the fracture toughness. Okay. So what is toughness? If you remember what earlier on in this paper 2, I was saying you've got to learn those definitions, learn all the definitions. Okay, for solid materials and things like that. Anyway, right, this is fracture toughness, and it actually tells you what it is. Fracture toughness is it's the energy absorbed on the impact. Okay, so here you have the difference in height between the start and the end is proportional to the energy absorbed on the impact. So that's the fracture toughness. Okay, so the toughness of a material is the maximum energy it can absorb just before it fractures. That's the definition of toughness. One of those definitions you need to learn. Right, difference in height between the start and end is proportional to the energy absorbed in the impact. Right, justify this statement. Okay, right, let's have a little look. Okay. So it starts from here. Okay. It's going to end up here. So those 2 lines, they're hopefully going to go through the center of mass of the hammer. That one looks pretty good. That one's okay. Right, so there you go. So it's this difference in height that we're after here, isn't it? Okay. That's going to be proportional to the energy lost on impact. Okay, because there's going to be some initial gravitational potential energy, and there's going to be some final GPE at the bottom. Okay, so 2 marks here, but yeah, I thought fairly straightforward. So the energy lost, the potential GPE lost, okay, is equal to the so it's the initial minus the final. Now that's going to be equal to the energy lost during fracture, isn't it? Now some of this is going to be going into actually breaking it. Okay, but some of this is going to be lost as sound. So a small amount is going to be lost as sound. Okay, but hopefully you can see there that roughly this value was actually going to be equal to that value, isn't it? If you take into consideration both the energy to break the sample and the energy lost as sound. Okay, so that was how I justified that one. Okay, so because the mass of the hammer and gravitational field strength are the same, then this fella is proportional to the change in height, isn't it? Okay, so the change in height, okay, is therefore proportional to the energy lost in the fracture. And I think that is what you were asked to justify, wasn't it? Okay, right. The hammer's released from a height of 13 centimeters above its lowest point in the swing. Calculate the momentum just before it hits the sample. Right. We want the momentum. We need the mass and the velocity. We know the mass, but we need to find the velocity. How are we going to find the velocity just before impact? Energy. Okay, so the energy lost, the energy GPE, the GPE lost is mgh. Now it's 13 centimeters, so it's 0.13 meters. So the GPE lost 35.53 joules. That's how much GPE is lost. Now we equate that to a half mv squared, don't we? A half times 31. Don't need to do anything with the 31. It's in standard units, which is nice. V squared equals 35.53. Okay. V squared comes out as 2.55. So V 1.597 meters per second. Okay, 1.597. So momentum P is mv. We're going to use the 31 again, multiplied by 1.597. That's 49.5. 0.5 kilograms ms to the minus 1. Not forgetting our unit, of course. Okay? Very straightforward. Right. The Titanic was a ship, a cruise ship that sank. There we go. Sketch shows the fracture toughness of a sample of steel as it varies with temperature. Okay. The Titanic sank in 1912 because it collided with an iceberg in the icy waters of the Atlantic. The steel hull of the ship was fractured by the impact. Deduce why the steel hull was likely to have been fractured by the impact. Well, obviously, the fracture impact drops rapidly with temperature. Now, what sort of temperature was the sea in where the iceberg was? Well, you might think, oh, well, 0 degrees C might be, but actually less than that, because salt water has a lower freezing point than fresh water, doesn't it? That's why when the roads are icy in the winter in cold countries, you have things called grit lorries driving around, sprinkling crushed rock salt on the road, because that melts the ice. The reason it melts the ice is because salty water has a slightly lower melting point, freezing point, than fresh water. It's actually about -2. So the fracture toughness of the hull of the Titanic, okay, is going to be about there. Now we're not given any units here, but we're just going to just describe what happens here. Okay, so we've got a rapid drop off in fracture toughness. So why has that caused the Titanic to sink? Well, obviously it's cold. The steel hull is colder, So the fracture toughness is quite a lot lower than normal. If the fracture toughness is lower, it can withstand less energy on impact before it fractures. And if you sail a ship into an iceberg, you're going to basically impart quite a lot of impact energy on the hull, which is going to be enough to break it and sink it. So, a very generous 3 marks there, I thought. Anyway, see you in the